Hello and welcome back to this demo on deploying using Canary deployment strategy to the container engine for Kubernetes cluster, leveraging OCI DevOps project. So let's continue with our setup. Now let's go ahead and start creating our build pipeline, for which we'll have to go to our DevOps project. Let me switch to the first tab and let me select. So currently I'm in my DevOps project and let me select the build pipeline. Click on create build pipeline and give this build pipeline a suitable name. Alright, so I have given name for my build pipeline. Let's click on create. Alright, so this brings us to the dashboard where we'll start creating different stages. So as we all know, the first stage is the manage build stage, which is the default stage that we must create. So let's click on add stage and click on the manage build stage and click on next. Enter the stage name. Description is optional. Let's leave everything as default. As mentioned earlier, if the build_spec.yaml file is not present in the root of your code repo, you must provide a relative path at this location. In our case, it's available in the root directory. Let's go ahead and add our primary code repository. Let's click on the select button. Choose the connection type as OCI code repo and select your code repository. Make sure the branch is selected as main and give your build source a name. Now let's save these changes. Alright, let me verify all the details. Everything looks good, so let's click on add. And as you can see, the manage build stage is added with the name build Python app. Now the next stage that we will add is the deliver artifact stage. So let's click on this plus icon over here. Click on add stage. Select the deliver artifact stage from the optional section and click on next. Give this stage a suitable name. Click on select artifacts to choose the artifacts you wish to deliver. So let's click on select artifacts and select both our artifacts, that is the Kubernetes manifest and the Docker image. So let's select both of these and click on add. Now it says associate the artifacts with the build result. So we must ensure here that the build config or the result artifact name should match with the one we have specified in the build_spec.yaml file. So let me take you to the build_spec.yaml file in my code repo. And if I open this file over here, if you scroll down to the output artifact stage, the name given for Docker image is OKE_app_base, and the one for the Kubernetes manifest is OKE_deploy_manifest. So let's use these names. Alright, so I've added both the names over here. Let me also give you a quick walkthrough of the build_spec.yaml file. So as you can see, we have the build_spec.yaml file with the exported variable set to as build run_hash, which we'll be using to generate the unique names for our image. And then in the input artifact, we are using the Golang CLI. And then within the steps, we have different commands where first we are defining the unique image tag for every image that we create out of this build run. And in the next step, what we're doing is we're using the docker build command to create a container image for our application. And then we have the output artifact stage where we'll be delivering those artifacts generated to the respective locations. Alright, so let's get back to the build pipeline. And now let's verify the details for our deliver artifact stage. Everything looks good to me, so let's click on add. Okay, so the push artifact or the deliver artifact stage is added. Now let's create the DevOps environment. So let's go to our DevOps project using the breadcrumb link. And now select the environments from the left menu. Let's create an environment. Make sure you choose the Oracle Kubernetes engine. So I've selected that. Let's give it a suitable name. And let's click on next. Now make sure you're in the right region and the right compartment. And now select the cluster that we had pre-created. So this is the one that we had pre-created. Let's select this and click on create environment. Alright, so our environment is successfully created. Now let's go back to the DevOps project. Now it's time to create our deployment pipeline. So let's click on the deployment pipelines from the left menu. Let's click on create pipeline. Give this pipeline a suitable name. Let's click on create pipeline. Alright, so as you can see, we have reached the dashboard where we can add stages to our deployment pipeline. So let's click on add stage. And this time we'll be using the canary strategy deployment option. So let's click on the canary strategy and click on next. Now let's fill up the details that are required. Make sure you select the deployment type as OKE. Give this stage a name. Select the environment that we had created in the DevOps project, which is OKE cluster. Provide a canary namespace. So let's give this canary namespace a name, NS canary stage. Now let's select the artifact. Alright, so we have to provide the Kubernetes manifest artifact. Let's click on that and click save. And if you recollect from the canary deployment strategy lesson, for the OKE deployment using canary strategy, Nginx ingress controller has to be set up, right? And we have already done that in our OKE cluster. We must also provide the Nginx ingress name that we are using. So let's provide this name. So we have already provided this name in our deployment file. Let me take you to our deployment file. So this is the deployment manifest. Let's click on it. And if you see in the deployment, we have defined ingress for our application. And let's copy this name. Let's use it over here. Verify all the details. For me, it looks good. So I'll click on next. Now, as we had studied in the theory lesson that you can have a validation control stage, which again is an optional stage where you can use a custom logic through a function to validate your rollouts. But for now, we're not using any validation control. So we'll select none and click on next. Now under the traffic shift stage, provide the name to this stage. Let me give it a name. So as we all had studied that this stage lets us shift a part of production traffic to the canary environment. So I've given it a name, canary percentage of shift, and let's give the ramp limit. So I've set the ramp limit to 25. Basically ramp limit is set in percentage, which specifies the maximum traffic to be shifted to the canary environment. We will validate this once we run our pipelines. So let's click on next. Now we have come to the approval stage. So this is the manual approval stage, right? Let's give it a name. And let's use 1 as number of approvals required to pass this stage. Let's click on next. Now we have reached the production canary stage. So here let's provide a suitable name to this stage. Alright, so I've given this stage a name, switch to production environment. The production environment is already selected, which is our OKE cluster. We have to provide a production namespace. So this time I'll use the namespace as NS canary prod. So let's use this as the namespace, NS canary PRD, and ensure that you check the auto rollback option, which will automatically roll back to the last successful version in case of any failures. So let's click on add. And as you can see, our canary stages are getting created. Alright, so it's done. Let's click on close and we can see them in our dashboard. Right, so once we have created this deployment pipeline, let's go back to our build pipeline and connect these two using the trigger deployment stage in the build pipeline. So let me go to the DevOps project, select the build pipelines, click on the build pipeline, and now let's add the trigger deployment stage. Let's click on the plus icon, click on add stage, and from the optional stages, select the trigger deployment stage, click on next, give this stage a name, and select the deployment pipeline. So this is the deployment pipeline that we had created. Let's select this and click on Save Changes. Alright, so let's validate all the details. Things look good to me. Let's click on Add. There you go. So our trigger deployment stage has been added to the build pipeline. Now there's one last thing that's left as part of this setup is to create the namespaces in our Kubernetes cluster. So let's go to our Cloud Shell. Let me clear the screen. And let's use the kubectl create ns command to create the two namespaces that we had defined in our pipelines. That is ns canary prd and ns canary stage. So I'll be using this command to create the namespaces, right? So let's go ahead and hit enter. Alright, so both the namespaces are created for us now. We can cross-validate using kubectl command. Using kubectl get ns. And as you can see, our ingress nginx namespace is present and the other two that we just deployed are present. And these are the system default namespaces. Alright, with this we have completed the entire setup to demonstrate the canary deployment strategy to deploy an application on the container engine for Kubernetes. I'll stop this video here. I'll see you in the next video where we will see the entire thing in action. Thank you for watching. Welcome back to this final part of deploying to OKE using canary deployment strategy. Now let's see the build and deployment pipelines in action. Let's go to our DevOps project. This is our build pipeline which we had created in the previous demos. Let's go ahead and start the manual run. So let me click on Start Manual Run over here. So this brings us to the Start Manual Run page. There's nothing to do over here. Let's click on Start Manual Run. Alright, so the manual run has successfully started. This window is divided into three sections. On the left hand side, we have this flowchart that indicates which stage is currently running and the next stage that would execute after the first one finishes. In the middle, we have this window which indicates the build run progress, and on the right hand side, we have the logs that will be displayed as and when the events progress. So the first thing that's happening is the manage build run stage is getting triggered, where we are building the Python application. So basically a build runner is getting provisioned, which will set up all the software in the build environment. It will download the source code from the code repositories we have provided, and then it will pass the build_spec.yaml file and execute all the commands within it. Now once the manage build stage executes successfully, it will trigger the deliver artifact stage, which will deliver the artifact, that is the container image and the Kubernetes manifest, to the respective locations. For the container image, let me take you to the container registry. So if you see the current repository that we had created for our container image, it has no image in this repository. Once the deliver artifact stage executes successfully, we will be able to see an image created in that repository. And again, like I always mention, you should check the logs in order to see what's happening. In case of errors and failures, these logs can help you troubleshoot. Alright, so the first stage, which is the manage build stage, has executed. As you can see, it's green. And now what's executing is the deliver artifact stage. Alright guys, so as you can see, the push artifacts or the deliver artifact stage has executed. Let me go to the container registry and refresh this repository, and you will see that the new image has been transferred to this repository that was just created a minute ago. Let's go back to the build pipeline and wait until it triggers the deployment pipeline. Alright, so as you can see, the trigger deployment pipeline stage has executed, and let's go to the deployment pipeline by clicking on the DevOps project and click on the deployment pipelines. Click on our deployment pipeline, click on deployments, And as you can see, there's one deployment in progress, which was triggered through the build pipeline. So let's click on this deployment. And as you can see, there are these stages in our deployment pipeline. The first stage, which is deployed to OKE, has executed already. The second stage is in progress. So the next stage, which is Canary OKE traffic shift stage, has also completed. For now, this is the first run of our application, so it doesn't matter. The next stage is the OKE deployment validation stage. Again, this is a manual approval stage. So let's click on these three dots over here and approve this stage. We're approving this stage since this is the first run of our application. So this is the first. Let's click on approve. Alright, so the approval is succeeded. And finally, it will deploy our application into the production environment. So if you remember, our production environment namespace was NS Canary prod. Alright, so all the stages have executed successfully and our application has been deployed in the production environment. To validate the application deployment, let's go to our Cloud Shell. Let me restore this. And I'll be running this command, which is basically a for loop, which switches between the two namespaces that we had created. One is the NS Canary prod and NS Canary stage. And it will use the kubectl command to get the pods and the ingresses within those namespaces. So let me hit enter. Alright, so as you can see, our NS Canary prod has our application deployed in it, right? And it also has an ingress load balancer's IP address, which we will be using to test our application. So let me copy this. Let's paste this IP over here. Alright, so as you can see, we have the application deployed to our production namespace with the version 0.1 and the message with love from OCI DevOps. Alright, so this was the first instance of our application that got deployed in both the NS Canary stage and NS Canary prod namespaces. Now what we'll be doing is we will be simulating a new release scenario for which we will go and edit our source code and make some changes to it. Alright, so let's go to our GitHub repository and make some changes in our Python application. So this is my GitHub repo. Let's go to the main.py file, which is in the root. So this is the Python application file. Let's click on this and let's edit it. So currently the version is 0.1. Let me change it to 0.2. And let's also change the message to DevOps team. And let's commit these changes. Alright, so I've committed the changes. Now, since this repository is mirrored in our DevOps code repository, let's go to our DevOps project and go to our code repository. Let me click on the DevOps project name. Let me select the code repositories. Basically, we are ensuring that the changes in our Python application have been mirrored in our code repository within the DevOps project. So let's select our code repository. Okay, so let's go to the main.py file and see if we have the updated code in the file. Alright, so we'll have to wait until the mirroring completes. Alright, so the mirroring process is complete now. Let's select the main.py file. Alright guys, so as you can see, the updated code is reflecting in the main.py file within our code repository. So now with these changes, we will be publishing a new release of our Python application using the Canary deployment. So let's go back to our build pipeline by clicking on the project name. Let's select the build pipeline. Let me select our build pipeline. Alright, so now what we will be doing is we'll be starting the build pipeline to create a new release of our Python application, which will be then sent to the deployment pipeline. So let's click on Start Manual Run. Alright, so let's click on the Start Manual Run button at the bottom. The manual run has successfully started. And it will repeat all the steps of creating our Python application with the new code. And then it will push the container image into the container registry repository that we have created. So at present, we have only one image, which is the first run of our application. Now, once this build pipeline executes, we will have another image created as a new version of our Python application. Let's go back to the build pipeline. So in the meanwhile, let me duplicate this tab and let's go to the deployment pipeline. Alright, so once the deployment pipeline is triggered, we will see an in progress new deployment over here. Let's go back to the build pipeline and wait until it completes. Alright, so the manage build stage has completed successfully. Now we are in the deliver artifact stage. Alright, so the deliver artifact stage has executed. If I go to the container registry and refresh this repository, you can see a new image is created and this will be used for the deployment purpose. Alright, so the trigger deployment stage has executed and let's go to the deployment pipeline now and see if a new deployment is triggered. Alright, a new deployment has triggered. So let's click on this. So it's executing the first stage of our deployment pipeline, which is Canary OKE deployment, and that has executed successfully. Now it's running the Canary OKE traffic shift stage, where we have diverted the 25% of traffic to the NS Canary stage namespace. So that stage is currently in progress. Alright, so that stage has executed successfully, which means now 25% of user traffic will be diverted to the new application. Alright, so to test this thing, let's go to the browser. And this is our ingress load balancer IP. Let's randomly refresh this IP. So as you can see, on random refreshes, we see some of our requests are going to the Canary stage. That is, we are getting the new versions, right? So I had added team and changed the version to 0.2. If I again refresh this, it's going to the previous version of our application. So basically on random refresh, 25% of the traffic is transferred to that new version that is deployed in the Canary environment. So to see this entire thing in a more detailed manner, let's go to the Cloud Shell. Let me clear the screen. So now let's run this custom command to see whether the traffic that's hitting this ingress load balancer IP is taking us to which of these environments, right? So as per the setup, 25% of the traffic must go to the new version and remaining 75% must go to the older version. Alright, so as you can see, most of the traffic is going to the previous version, that is 0.1, right? And few of the traffics in between, as you can see, is going to 0.2 version, which is deployed in the NS Canary stage, and the 0.1 version is deployed in the NS Canary prod namespace, right? So these are the two environments. This is the Canary environment where the latest releases will be put, and you need to test it against normal user traffic with limited user traffic. And this is the NS Canary prod namespace where you will push your new release once you provide a manual approval, which then replaces the older version. So at present, the Canary OKE traffic shift stage is in action, which is letting only 25% of the traffic to reach our newly deployed application in the NS Canary stage namespace. So now we must give the manual approval to shift the application to the NS Canary prod namespace. Right, so let's click on these three dots and click on approve. Give the reason for approval, test passed, and click on approve. As you can see, the approval stage has completed successfully. Now it will deploy the application to the production namespace, which is NS Canary prod namespace. As you can see, it's applying the Kubernetes manifest and checking the deployment status. That's done. So let's go back to our Cloud Shell and rerun this command. Let me clear the screen. And this time you'll see that the entire traffic is now going to the version 2, which is 0.2 that we had deployed. And now the 0.2 version of our application is deployed in the NS Canary prod namespace within the OKE environment. Similarly, if we hit that URL through the browser, and now if I do refresh, it will always go to the latest version deployed. Alright, so with this we have understood how a canary deployment strategy works. There's one more thing that's left for me to show is the rollback option. So let's go to the last stage, click on these three dots, and there's an option to manually roll back your deployment to the previous release. So let's click on manual rollback. Alright, so this brings us to the manual rollback page, and we must select the deployment that we want to roll back to. So click on select deployment. Since we had only one previous deployment, let's select that and click on save change. And once you click the rollback stage, your deployment will be rolled back to the previous version of your application, which is 0.1 in our case. Let's click on rollback stage. The rollback has started. So we'll wait for the rollback to complete and validate the deployed application. Alright, so the rollback has completed successfully. Now let's go back to our application, and this time if we hit refresh, and we can see that the deployment has been rolled back to the previous version of our application, which is 0.1. If I hit multiple refreshes, it will still go to 0.1. Similarly, if you want to see the same through that customize command, let me clear the screen and hit enter. As you can see, and now we have the previous version of our application deployed in the ns-canary prod namespace. So with this, we come to the end of this demo on how to use canary deployment strategy to deploy applications on OKE clusters. I hope you enjoyed all the three demos. See you in the next one. Thanks for watching. Hello and welcome to this lesson on Helm Overview. I am Mahendra Mehra and I am a senior training lead and evangelist with Oracle University. So what basically is Helm? A typical application deployed to Kubernetes will have objects such as deployments, services, secrets, persistent volumes, persistent volume claims, ingress, and so on. And with its declarative nature, you define everything through the YAML files. When we deploy application to Kubernetes cluster, we may need to create multiple services. A large application can contain more than 40 microservices, and each service can contain multiple Kubernetes resources such as service, deployment, secrets, etc. Now imagine the same application needs to be deployed in different environments such as test, QA, and prod environment, with configurations meeting those environment specifications. It will get very cumbersome and inefficient to deploy the Kubernetes resources one by one based on the YAML files. Also, these YAML files are extremely complicated to maintain and prone to errors. So the question arises, do we have a more efficient way to manage these Kubernetes resources files? The answer is yes. You can use Helm chart package to create and manage your applications based on the chart package through the Helm command. Helm helps you manage Kubernetes applications, and Helm charts help you define, install, and upgrade even the most complex Kubernetes application. Consider Helm for Kubernetes just the way we have pip for Python and yum for CentOS. Helm is an official Kubernetes project and is part of the Cloud Native Computing Foundation. Let's take a look at the Helm architecture. The core is the Helm client and the Helm chart package. The Helm command can download the Helm chart package from the repository and read the kubeconfig file and construct HTTP requests for Kube API server REST API interface. By calling the REST API interface provided by Kubernetes, all the Kubernetes resources that are defined in the YAML format contained within the chart package are created in the Kubernetes ecosystem. The latest version of Helm is Helm version 3 as I record this video. To better understand Helm, there are three concepts we need to get familiar with. The first one is the Helm chart. The Helm chart represents a Helm package. It contains all the resource definition files in YAML format needed to run an application, tool, or service. A chart usually comes with default configuration values in its values.yaml file. Some applications may be fully default values, but you will typically need to override some of the configuration to meet your needs. The next concept is release. A release is an instance of a chart running in the Kubernetes cluster. One chart can often be installed many times into the same cluster. Each time it is installed, a new release is created. Consider a WordPress chart. If you want two WordPress running in your cluster, you can install that chart twice. Each one will have its own release, which will in turn have its own release name. For example, if we run helm install a WordPress, release A is created. And if we reinstall the same package as helm install B WordPress, a new release B is created. The third concept is the chart repository. Similar to GitHub repository, where source code is maintained, and Docker Hub, where images are stored, chart repository is a place to store and share Helm charts. Helm search hub command searches through the artifact hub from the dozens of repositories. You can add custom repositories in the local Helm client using the helm repo add command and search through these repositories using the helm search repo command. So as you can see from the example, I've added a custom repository using the helm repo add bitnami command. Bitnami is my custom repository, and then I am using the helm search repo to search into the bitnami repository for the WordPress chart. To wrap up, in this lesson we realized the importance of Helm and covered its architecture along with three basic concepts like Helm chart, release, and chart repository. I hope you liked the video. See you in the next lesson. Thanks for watching. Hello and welcome to this lesson on Helm chart structure and basic commands. I am Mahendra Mehra and I am a senior training lead and evangelist with Oracle University. Helm packages are called charts and they consist of a few YAML configuration files and some templates that are rendered into Kubernetes manifest files. Let's understand the basic directory structure of a chart and their functions. So the first directory that we're talking about is templates. This directory contains template files that are combined with the configuration values and rendered into the Kubernetes manifest like deployment, service, etc. The templates use the Go programming language's template format. The next file is the values.yaml file. This is the file that holds the default configuration values for the template files. Next is the chart.yaml file. It is a YAML file with metadata about chart, such as the chart name and version, maintainer information, a relevant website, charts dependencies, and search keywords. The license file is a plain text license for the chart. We also have a readme.md file, which is basically a file with information for users of the chart. And we have the charts directory. Manually managed chart dependencies can be placed in this directory. Charts can also contain files that describes the installation, configuration, usage, and license of a chart. In Helm, it can be understood that it mainly contains two types of files: template files and configuration files. There are usually multiple template files and one configuration file. Make a note, a template directive is enclosed in double opening and closing curly brackets. Helm template provides powerful template rendering capabilities, and Helm can render the values in the configuration file into the template files. And finally, generate a resource definition file. Let's take a look at some of the basic Helm commands. The Helm install command will install a chart from a repository, so you should ensure that you have set up the repository first. The Helm list command will help you see all the charts that have been deployed on your cluster. The Helm upgrade command upgrades your release with new values and provides a new revision number to your existing release. The Helm rollback command is used to roll back a release to a previous revision. The first argument of the rollback command is the name of the release, and the second is a revision version number. If this argument is omitted, it will roll back to the previous release. And we have the Helm uninstall command. This command takes a release name and uninstalls the release. It removes all the resources associated with the last release of the chart as well as the release history, freeing it up for future use. Also remember, the values.yaml file is very important for templates. This file contains the default values for a chart. These values may be overridden by users during Helm install or Helm upgrade command. To wrap up, in this lesson we discussed Helm chart structure in detail and covered basic Helm commands to help you start with Helm. I hope you found this lesson useful. See you in the next lesson. Thanks for watching. Hello and welcome to this part 1 demo on Helm basic commands. My name is Mahendra Mehra and I am a senior training lead and evangelist with Oracle University. So let's get started. So before we move on to the console to practice the Helm commands, let's quickly do a recap on the Helm architecture. So as you can see, we have a Helm client, which is basically a command line client for the end users, and it is responsible for local chart development, managing repositories, managing various releases, and again it interfaces with the Helm library that helps you send charts to be installed, also requesting upgrading or uninstalling of existing releases. This Helm library provides the logic for executing all the Helm operations. Basically, it interfaces with the Kubernetes API server and provides us the capability to combine a chart and configuration to build a release. It also helps us to install charts into the Kubernetes and provide subsequent release objects. It helps us upgrading and uninstalling charts by interacting with the Kubernetes server. Alright, so with this information, let's get to the OCI console and start exploring Helm commands. Okay, so I have logged into the OCI console, and for this demo, we will be using the Cloud Shell, which comes pre-installed with Helm 3, Docker, and kubectl. You can also practice these commands from within a compute instance SSH session. All you need to do is install Helm package using the yum package manager. Also, you can practice Helm commands using your local machines, provided that you have installed the Helm packages. Kindly note, in the interest of time, I have already set up prerequisites that would be required for us to move on with the demo. That is, I have already configured an OKE cluster and have set up the Cloud Shell access to it. So let me quickly show you the OKE cluster that I have pre-created. Let me go to the developer service, click on Kubernetes cluster. And as you can see, I have the OKE cluster pre-created. This is the cluster where our Helm client will be installing all the charts and creating all those releases. Alright, so let me quickly jump to the Cloud Shell. Let me maximize the screen. Alright, so we have the Cloud Shell running and there's the prompt where we'll be writing all the Helm commands. Alright, so let me show you that we have the cluster access using the Cloud Shell by typing the kubectl command. Kubectl get nodes. And as you can see, our cluster access is available and we are connected to the cluster that I have created using the OCI OKE service. Alright, so the first command that I'll be running is the Helm version command. So Helm version, this command basically prints a representation of the version of Helm, and the output, as you can see, reads the version number of the Helm. So the current version is version 3.7.1. You can also see a git commit. Basically, this is the SHA for the commit that this version was built from. And then you have the git tree state, which is clean. That means there are no local code changes when this binary was built. Again, if its status is dirty, it means that the binary was built from a locally modified code. And again, the Git client uses Go language, so the Go version is Go version 1.17.5, which was used to compile this Helm. So let's move on to the next command, which is Helm list. What this command does is it lists all the releases for a specified namespace. As you can see, currently there are no releases or no Helm chart installed on our Kubernetes cluster, so the output is nil, right? And what it does is it helps you display all the releases that are deployed or failed within your Kubernetes cluster. Okay, so the next command is Helm search hub command, and then you have to pass the chart name that you want to search within the hub, right? So let's say I want to search for a WordPress chart, and let me hit enter. So as you can see, these are the many charts related to WordPress that are available on the Artifact Hub. Now, what is Artifact Hub? Basically, Artifact Hub is a web-based application that enables finding, installing, and publishing packages and configurations basically for the CNCF projects, which includes publicly available distributed charts, also called as Helm charts. And it's basically a cloud-native computing foundation CNCF sandbox project, which you can browse at artifacthub.io. Let me take you to artifacthub.io. So as you can see, this is the hub where you will find all the charts that are available from different contributors, right? And this is the hub where the Helm search hub command searches into for a particular chart that we pass as one of the arguments. Okay. All right. So let me quickly clear my screen. And then the next command is the Helm repo command. So if I do a Helm repo list command, it will list all the repos that are currently available within the Helm client. So let's say I have this chart repository which I want to delete. So in order to delete an existing chart repository, what you can do is you can use Helm repo remove command. You can use the Helm repo remove command and specify the name of the chart repository. So let's say I want to remove Bitnami. And if I hit enter, it removes the Bitnami chart repository. And if I do a Helm repo list again, the Bitnami chart repository is deleted. Again, if you wish to search for a chart within these repositories and don't wish to go to the hub, you can use the Helm search repo command and pass the chart name as the argument that you're looking for. So let's say I want to look for WordPress chart. As you can see, the Helm search repo WordPress has come out with no results. That's because the WordPress chart isn't available in any of these chart repositories. And the WordPress is part of the Bitnami project. And since the Bitnami chart repository was deleted earlier, let me quickly show you how to add a chart repository to your Helm client. So the command is Helm repo add name of the chart repository and the URL where the chart exists. Okay, so let me quickly go and enter. And there you go. The Bitnami has been added to our repositories. Now if I do a Helm list, so we have to go for the Helm repo list command. And as you can see, now we have the Bitnami chart added to our repository. All right. So let me quickly clear the screen. And now if I do a Helm search within the repo for the WordPress, you can see we have the WordPress chart available and the chart version and the app version. All right, so now that we have located the WordPress chart within the Bitnami repository, let's move on and install the WordPress chart in our Kubernetes cluster. So the command for which is helm install WordPress-OCI-demo space the name of the chart that you wish to install. All right, so the WordPress-OCI-demo is the release name. So let me go ahead and hit enter. So as you can see, our Helm chart has been installed, and as you can see from the information, the release name is WordPress-OCI-demo, and the chart name is WordPress, and these are the versions. And the revision for this release is 1. And as you can see, there are instructions given here in order to access the WordPress website that we have just installed on our Kubernetes cluster. So let's access the WordPress website that we have deployed, for which I'll be running this kubectl command in order to get the load balancer's IP. So let me copy this and paste it over here. Alright, so as you can see, the external IP allocated to our load balancer is this. I'll copy it and let's paste it over here. There you go. So as you can see, our WordPress website has been deployed on the Kubernetes cluster, and this is the landing page. Now, if you want the admin access to this WordPress website, as you can see from the output, we can also have the admin access, right? So I'll have to just provide the /admin in the URL. And which brings me to the login page. Again, the login credentials are available over here. As you can see, the username is user and the password is available. So let me quickly just first grab the password. Let me press a Ctrl+C over here to come back to the prompt and get the password to our admin user. Alright, so this is the password and this is the username. Let me copy the username. And let me copy the password. Alright, so we've provided both the username and the password. Let's log in. There you go. So this is the dashboard for the admin, where we can now go ahead and create posts and do different stuff with the WordPress website. Alright, then with this we have installed a WordPress website using the Helm chart from the Bitnami WordPress chart repository. Let me make some space on the screen here and let me show you the Helm list command now. So if I do a Helm list now, what we'll be able to see is the release that we have just configured on the Kubernetes cluster, that is the WordPress-OCI-demo, and it's installed in the default namespace. The current revision is 1 and the status is deployed, right? So this is the information that you get now using the Helm list. Let me also show you that the pods and the deployment is created on our Kubernetes cluster using the kubectl commands. So kubectl get pods will show us that the WordPress pods are created. You can see there are 2 WordPress pods that are created. One is the database and one is the front end. And if you wish to see the deployment, we can use the kubectl get deploy command. And that's the deployment, which is in the ready state. Alright then, so with this, we come to the end of this demo. I hope you liked this demo. See you in the part 2 of the Helm basic commands. Thanks for watching. Hello and welcome to this demo on part 2 of Helm basic commands. In this video, we will see how to create a Helm chart, view the Helm chart structure, and perform Helm upgrade, rollback, and uninstall a Helm chart. So let's get started. So I'm back to my Cloud Shell prompt, so let's begin. The first command that I'll be showing you is the Helm create command. Okay, so this command creates a chart directory along with the common files and directories used in a chart. So it has done creating a directory called demo-nginx, which will contain all the Helm charts and the common files. So in order to see the Helm directory structure for the demo-nginx and all the common files within it, let me open up the code editor. You can access the code editor from the top right section. In the meanwhile, I'll also show it to you on the shell. So let me quickly go into the demo-nginx directory and do an ls over here. So as you can see, these are all the files that we have within the demo-nginx Helm directory. Okay, so the code editor is up. And as you can see, these are the list of directories that are present in my home directory, amongst which we have this demo-nginx that was created when we did the helm create command. And let me go into this demo-nginx directory to see the helm chart directory structure. And as you can see, we have the values.yaml file, the chart.yaml file, we have the templates directory and the charts directory. So let me open up the values.yaml file for you. And as you can see, it contains all the values that it will be imported within the Kubernetes manifest files. As you can see, the service type is set to be cluster IP, the port is port 80, and there are different values that you can configure within the values.yaml file. For example, there's this replica count, which is set to 1. Right. At the same time, if I take you to the deployment.yaml file, which will be available within the templates directory. So if I expand the templates directory, you can see we have different Kubernetes templates available here. And one of it is the deployment.yaml file. Let me open it up for you. And this is the deployment.yaml file, which contains all the metadata and the spec section, which imports its values from the values.yaml file, which I showed you earlier. So let me minimize this code editor window and let's jump back to the Cloud Shell. So now let's install this Helm chart, for which I'll just come out of this Helm directory and use the Helm install command. And this time around, I am using the Helm install command by specifying the path to the unpacked chart directory. And the --values flag is used to specify the values.yaml file to be used for this Helm chart deployment. And test-helm is the name of the release. Okay, so let me go ahead and hit enter. All right, so the Helm chart has been deployed. As you can see, the status says deployed. The revision is 1, since this is the fresh install. And the name of our release is test-helm. And it also has given us some instructions to follow in order to access the application that we have just deployed. So let me quickly use these instructions. Firstly, I'll be exporting the pod name into the pod_name variable. So let me copy this and paste this here. The next thing is I have to export the container port. So let me copy this. And then we'll be using the kubectl command to port forward port 8080 to our container port. So let me just copy this, paste it here. All right, so the port forwarding has been done from port 8080 to port 80. Let me duplicate this tab to have a second instance of Cloud Shell. All right, so in order to access this URL, I'll be using the second Cloud Shell instance, and I'll be using the curl command to access that URL. So let me just copy this and paste this over here. As you can see, our Nginx application is accessible using the curl command. So you must be wondering, why aren't we using a public IP in order to access our Nginx application? That's because the service type, if you remember, in the values.yaml file was set to cluster IP. So now what we will do is go to the values.yaml file and make some changes there. So let me go back to the first tab and maximize this window. As you can see, we have this values.yaml file. As the current replica count is set to 1. If I go back here and show you the replica count, so let me do a kubectl. As you can see, our test-helm-demo-nginx deployment is ready. Let's see more detail about this deployment. So I can use the kubectl describe deploy and the deployment name. So if you see from the deployment information, we can see that the replica count is set to 1. And again, if I use the kubectl get svc command to check the services deployed, for the test-helm-demo-nginx deployment, the type of service is cluster IP, and again we don't have an external IP assigned to it since it's cluster IP. So what we will be doing now is we'll go back to the values.yaml file and we will change the type from cluster IP to load balancer so that we get an external IP for it. And we'll also try to change the replica count so that we can see more replicas available. All right, so let's jump here to the previous tab and let me quickly change the replica count in the values.yaml file. Let's make it 3. And if we go down over here under the services section, I'll change the cluster IP to load balancer. Right, and let me save this file. So now that I've made changes to the values.yaml file, what we will be doing is now we will be, and let me close this port forwarding. Let me do a Control-C over here and clear the screen. Now that we have changed the values.yaml file, for those changes to take effect on the current release, we'll have to do a Helm upgrade command. So before I run the Helm upgrade command, let me do a Helm list to show you the current charts that are deployed and the revisions for them. So currently there are 2 charts that are deployed on our Kubernetes cluster. The one that we are dealing with right now is the test-helm chart and the revision is 1. Now that I've made changes to the values.yaml file, we'll be running the Helm upgrade command to upgrade the current release. Right, so let's run the command. So the command is Helm upgrade name of the release and path to the unpacked chart directory, and $value is specifying the path to the values.yaml file to be used. Right, so let's hit enter. As we can see from the output, the release test-helm has been upgraded and the revision is set to 2. Now there are different instructions as we can see as compared to the previous one. This time it's the load balancer that has been deployed. Right, so in order to access our application, we can use the load balancer's IP. In order to get the load balancer IP, we will use the kubectl command that's displayed over here. Let's just copy this. And let me hit enter. There you go. So this is the external IP that we have received now to access our Nginx website. So let me copy this and open up a new tab, paste the IP over here. So there you go. Now we can access the Nginx application on the Kubernetes cluster since we have changed the service type to load balancer. Right, and again, there's one more thing that I need to show to you is whether we have also increased the replica count. So let me again run this command, kubectl describe the deployment. Now if you see, the number of replicas is set to 3, which was desired. 3 has been updated and total 3 are available. So we have even managed to change the replica count and managed to change the service type to load balancer. So if I run the kubectl get svc command now, we will see for the Helm deployment, that is test-helm-demo-nginx, the type has changed to load balancer now, and we have received an external IP to connect to our application. So let me quickly clear the screen over here. So the next important command that I want to cover is the Helm history command. Basically, it prints the historical revisions of a given release. So let me write Helm history for the test-helm release. And from the output, we can notice that there are 2 revisions for this release. The status of the first one says it's superseded, and we have the second revision which is currently deployed. Right, and the description says upgrade complete, which means the second one is an upgrade to the first one. Alright, so now let's try the Helm rollback command. What this command basically does is it rolls back a release to a previous revision. The first argument of the rollback command is the name of the release. So let's write the rollback command. The name of the release is test-helm. And the second argument that we need to provide here is the revision number that we wish to roll back to. If you don't provide a revision number, it will roll back to the previous release. So let's provide the revision number here as 1. and hit enter. So the rollback was a success. Now if I do Helm history, as you can see from the output, the revisions have changed to 3, and currently 3rd is the active revision, where what has been done is we have rolled back the 2nd revision back to 1. So every time you do a rollback or an upgrade, you get a new revision created against that Helm release. Okay. Now from this rollback operation, what has happened is we have rolled back the 2nd revision back to 1, and under revision 1, the type of service was cluster IP, which means now the load balancer IP will no longer be effective. So if I go back to the tab where we had opened up the load balancer IP, and if I hit enter, as you can see, the page is not loading. Let me open up another tab and paste this IP over here. As you can see, the application is not responsive as of now. We can use the helm get values command followed by the release name to print the values file. So let me print the current values file for the test-helm release, which should be the values file that we had in revision 1. Alright, so from the output we can see that the service type is cluster IP, which was the value when we used the revision 1. And again, the replica count was 1 in revision 1. Alright, so let me run the helm list command. From the output, we can see that the test-helm release has 3 revisions to it, and the WordPress-OCI-demo release that we had created in the previous demo has only 1 revision. So now let's go to the last command, which is the helm uninstall command. What this command does is it takes release name as an argument and uninstalls that release. It removes all of the resources associated with the last release of the chart as well as the release history, freeing it up for future use. So let's run the helm uninstall command for both of our releases, that is test-helm first. So the test-helm is uninstalled. Now if I do an helm list, we won't find the entry for test-helm. As you can see, the WordPress is already running. Now if I uninstall this release using the helm uninstall command, alright, so the release WordPress-OCI-demo has been uninstalled. Now if you go back to this tab and try to refresh, so if I click on any of these links, the page is not responsive. So with this, we come to the end of this demo. I hope you liked the Helm Basic Commands demo, and I urge you to work with the command line often and learn the shorthand flags available in the help sections, which you can access by running the helm -help command. So see you in the next video. Thanks for watching. Hello and welcome to this lesson on Helm chart deployments to OKE. I am Mahendra Mehra and I am a senior training lead and evangelist with Oracle University. OCI DevOps service supports deployment of Helm charts to Container Engine for Kubernetes clusters. This new feature of OCI DevOps service enables developers to easily create continuous integration and delivery pipelines that includes Helm chart package deployments to their OKE clusters. Now, developers can add a specific Helm chart stage to the deployment pipelines to automate the Helm deployment and automatically roll back on OKE environments. Let's take a look at few key points to note before you execute the Helm chart deployment to OKE. Before you begin, you must create a container engine for Kubernetes cluster, and you can deploy to both public and private OKE clusters. You can build your Helm chart in a DevOps build pipeline and then push it to the OCI container registry to use in your deployment. You can also push Helm charts to a container registry if it is compatible with the Open Container Initiative. The Helm charts must be located in the OCI container registry repository for deployment. And lastly, Helm chart contains templates of Kubernetes YAML manifest files and a values.yaml file to supply the default template values. The values.yaml is a generic file that is located in the OCI artifact registry. You must create a reference to this file. To wrap up, in this lesson, we discussed the OCI DevOps service feature called Helm chart deployments to OKE, which makes it easier for developers to build, test, and then deploy their application release using Helm charts. I hope you liked the video. See you in the next lesson. Thanks for watching. Hello and welcome to this demo on using Helm with OCI DevOps to deploy to Container Engine for Kubernetes. I am Mahendra Mehra and I am a Senior Training Lead and Evangelist with Oracle University. So let me give you a quick overview of what to expect from this demo. In this demo, we will build a container image for a sample Node.js application. We will store it in a container registry to be later deployed to the Oracle Container Engine for Kubernetes, also known as OKE, via Helm charts. And all of this will be executed by leveraging the resources which are available in the OCI DevOps project. In the interest of time, I have already created a few resources which I'll be using during this demo. So let's get started. Alright, so I've logged in into the OCI console. Let me show you the resources which I have pre-created, which includes Kubernetes cluster and a GitHub personal access token as a secret inside the vault. Alright, so let me go to the hamburger menu, click on the developer services, show you the Kubernetes cluster that's pre-created. So this is the Kubernetes cluster, Mr-DevOps-Helm-OKE, which we'll be using to deploy the Helm chart into the OKE cluster. And then I have also created a personal access token secret. So let me go to the identity and security, click on vault. And this is the compartment where I'm performing all the demos. So keep a note of it that when you are trying to do it, you make sure all your resources are created in the same compartment. In my case, it's ctdoc. And if I show you the vault that I've created, which is DevOps demo. So I've created a secret under it called GitHub-pat, which basically stores my personal access token from my GitHub repository, which I'll be mirroring during the demo. Okay, then, so let's go back to the main console and let's spin up the Cloud Shell. Okay, so the Cloud Shell is up. Let me also set up the cluster access. So to set up the cluster access, I'll go to the developer service, click on Kubernetes cluster, click on my cluster name and select the access cluster button. You get two options, using Cloud Shell access or using local access. We will be going with the Cloud Shell access. So just need to copy this command and paste it in the Cloud Shell. So I'll maximize the screen over here. Let me go ahead and paste this. Alright, so the kubeconfig file has been written and I have the access to the Kubernetes cluster from this Cloud Shell. To reconfirm if I have the access or not, I'll use the kubectl command, get nodes. And there you go, I can see the nodes are accessible of my Kubernetes cluster. Okay then, so let's begin with the first task for this demo. Let me quickly minimize this Cloud Shell. So the first task is to create a DevOps project. So in order to create the DevOps project, I'll click on the hamburger menu and go to the developer services where I have the option to create DevOps project. So click on projects over here. Now I have to select the create DevOps project button and give your project a suitable name. In my case, I've given it Mr-DevOps-Helm, and you can give a suitable description if you wish. So let me give it a description. We will also have to select a topic which the DevOps service will use to send messages to the notification topic for the important events that will happen when we run those deployment and build pipelines. So let's select the topic. As you can see, currently under my compartment, there are no topics available. So in order to create a topic, I'll go to the observability and management section, where I'll have to select the notifications and create a topic under my compartment. So let's click on create topic, give it a name. The description is optional, so I'll leave it blank and click on create. Okay, so now that I've created the topic, let me go back to the DevOps project. And click on create DevOps. I'll have to redo this. Mr. Hyphen. This time if I select topic, you can see the drop down has auto populated the topic that I created. And let's select topic and click on create DevOps project. And again, what we'll have to do is we'll have to enable logging. So click on enable log and just enable this slider to enable the logs. So it says you have to select the log group and all. So we'll just leave it to default and click on enable logs. All right, so the DevOps log is created. And if we go back to the DevOps project, we can see that the DevOps project is created and is in active state. All right, so let me go inside this project again. And the first thing that we will do is we will create a code repository for this project. So let me click on Code Repositories. And like I said, I'll be mirroring one of my code repositories for this particular demo. So I'll use the mirror repository option. Let's select the connection and click on create connection. Give your connection a name. So let's say that's the name I've given for my connection, and the type is GitHub. Again, we need to provide the secret where we have stored the GitHub personal access token so that the mirroring can take place. So let me select the vault and let me select the secret, that is GitHub-pat, and let's click on create. Now if you click on the repository section, you can see all the repositories that are available within your GitHub repo. And I'll be using the helm-oci-devops node service repository because the code for this particular demo is available under this repo. So I'll just select this. You can also choose a mirroring schedule, and there are different types like once, default, and custom. I'll leave it to default. And then again, you can give a name to your connection. So I'll leave it to the default that's generated and click on mirror repository. All right, so as you can see, the mirroring is in progress, and in some time we will be able to see all the files from the repository that I just mirrored. In the meanwhile, I'll take you to my repository. So these are all the files that are present in the Helm OCI DevOps node service, and all these files will be mirrored in my DevOps code repository. So this process does take some time, and I'll just skip that part. All right, so as you can see, all the files have been mirrored in my GitHub repo, and we can see all the files over here. Right, so if I click on files, I can see all the files, page 1 and page 2. All right, then, so let's move on to the next task now. The next task is to set up our build pipeline. So let me go back to the DevOps project from the breadcrumb menu, and let me select the DevOps project and click on build pipelines. Let's create the build pipeline and give it a name. I leave the description blank and click on create. So this brings us to the dashboard where we can create all our build stages. Let's click on add stage to create the first mandatory stage, which is the manage build stage, and click on next. Let's give this stage a name. So the name that I've given is manage build step, and let's leave everything default. The next thing that you have to specify is the build_spec.yaml file's location. Now, if the location of your build_spec.yaml is in the root of your code repository, you just have to leave it as it is. Otherwise, you have to provide the relative path. The next thing that we'll be doing is configure the primary code repository. So click on select. Select the connection type, which is OCI code repository, and then select the connection that we created. Select the branch as main and provide the build source name. that you have used in the build underscore spec.yaml file. So in our case, it's node underscore express, and click on save changes. So with this, we are done creating our first stage. Click on add, and our first stage is added on the dashboard. So for better understanding, let me do a walkthrough of the build underscore spec.yaml file. So let me go to the GitHub repo, and if I open the build underscore spec.yaml file, as you can see, we have this exported variables named as build run underscore hash, which will be exported as a parameter or available as a parameter in the successor build pipeline stages. Again, under the steps, as you can see, there are different steps, and every step has a command that will be executing certain operations. So for the first one, we have define image tag, which will be using the build run underscore hash variable. Then we have install node prerequisites, which will be installing all the node prerequisites since it's a Node.js application. Then we have the npm install step. So the next command is helm build, where we'll be building the helm charts and all, and we'll be pushing them into the helm repository using the helm registry login and then helm push command. The other thing that we have here is building a container image, and then under the output artifacts section, we have created a name called application underscore docker underscore image, which will be used to transfer the container image at this particular location. Right, so this is all about our build underscore spec.yaml file. Again, another thing to note here is that we have this node underscore express location that we will be using on the build VM, from where all the codes will be used in different commands that we have laid out. Right, so that's why we specified node underscore express as the build source name when we were creating the build pipeline. Alright, so the next step now is to create a container registry repository which will hold our container image for the Node.js application. So in order to do that, we'll have to go to the container registry service. Let me duplicate this tab. Let me click on the hamburger menu and go to the developer service. Select the container registry and make sure you're in the right compartment where all your DevOps resources are being created. And let me click on create repository. Let me give my repository a name. Now remember, the repository name should be similar to the one that is mentioned in your build underscore spec.yaml file. So if I go to the build underscore spec.yaml file, the location is node -express -getting -starter. So I'll use this. And for this demo, I'm setting the access type as public and click on create repository. Alright, so my repository has been created. Currently, there is no image in this repository. Alright, so let's move on to the next task. The next task is to create a container registry for our Helm repository, right? So as you know from the build underscore spec.yaml file, we also have a Helm chart that is being built under the manage build pipeline, and it will be pushing the Helm chart artifacts to a Helm repository. So for that, we will have to create a Helm repository, and let's click on create repository. Give our repository a name. So the repository name is helm-repo/node-service, and make sure that the access type of this repository is again set to public. Click on create repository. So our repository is created. So now we have two repositories created. One is the node-express-getting-starter, which is for our container image for the Node.js application, and the other one is the helm-repo/node-service for our Helm charts. Now, since this video is already getting too long, let's cut this demonstration here and see you in the next video where we'll resume with the other tasks. Hey guys, so welcome back, and let's resume from where we left in the previous video. So the next task is to create a DevOps artifact for the container image repositories that we just created. So in order to create the DevOps artifact, we'll have to go to the DevOps project. Let me go back to the DevOps project and click on the artifact section. So in order to create the DevOps artifact, we'll have to go to the DevOps project. Let me go back to the DevOps project and click on the artifact section on the left hand side. So remember, the version of the container image that will be delivered to the OCI repository is defined by a parameter in the artifact URI that matches a build spec exported variable. So if you remember, the build_spec.yaml file has an exported variable by the name build_run_hash. You can also specify the name in the build pipeline parameter. We will be taking a look at it in the later stage. Alright, so let's start by creating a DevOps artifact to point to the container registry repository location we created in the previous video. So let me click on add artifact and let's give this artifact a name. Select the type as container image repository, and you need to provide the fully qualified path to your image in the container registry. So the fully qualified path for our image repository is IAD, which is the region key .ocir.io / the tenancy namespace / the repository name. So we have to make sure that the allow parameterization is enabled so that it lets us replace parameters used in this artifact. So what I'm going to do is I'm going to modify the fully qualified path to our image in the container registry and add a parameter name, which is basically the tag value. So I'm adding this $, within the curly braces, the parameter name, that is build_run_hash, and this has come from the build_spec.yaml file. So if I take you to the build_spec.yaml file, you see that the exported variable has build_run_hash as an exported variable, which will be used as a parameter, right? So that's what we have set over here. So with this, let's click on add, and we have added an artifact for our container image repository, right? And now let's add another artifact for our Helm repository. So let's click on add artifact, give it a name. Now this time around, the type is Helm chart, since we are storing Helm chart within that repository. So I'll select the type as Helm chart. You have to provide the URL for your Helm chart. So the URL is, so notice that the URL is a bit different from what we used to specify in the container image repository path. Here we have OCI : / followed by the region key and OCIR.io / the tenancy namespace / the repository name. Right, so don't miss out on this. That is OCI : /. Alright, so let's also fill the version, which is 0.1.0- and the parameter name. Again, this is the parameter that will be auto populated once the build is run. Click on add. So now two artifacts are added. One is for the OCI registry, which is the image registry, and one is for the Helm chart. So if you remember from the Helm demos, Helm uses a values.yaml file, and usually that values.yaml file is available in the Helm folder. So DevOps project provides you an option to override that values.yaml file, which is available in the Helm folder, by specifying it as an artifact under the DevOps project. So what we'll be doing is we'll be creating a values.yaml artifact, which will override the one that is available in the Helm folder. To do that, click on add artifact, enter the name as values.yaml, and select the type as general artifact. Now select the artifact source as inline and provide the definition for the values.yaml file. So this values.yaml file will set replica count as 3 and set the service type as load balancer for the public IP address to get assigned. So ensure that you set the allow parameterization to enable to help replace parameters used in this artifact. Let me go ahead and click on add. So now that we have defined all the artifacts, let's jump back to our DevOps project, build pipeline, and create another stage called deliver artifact. Let me select the build pipeline. So let's click on this plus icon to add a stage, and this time we'll be adding the deliver artifact stage. So this deliver artifact stage will map the output artifacts from the manage build stage with the versions to deliver to a DevOps artifact resource and then to the OCI repository. So let's click on deliver artifact and click on next. Give the stage a name. Select artifact, and from the artifact we'll select the Docker image artifact and click on add. Alright, so it says associate artifacts with build result. So the value over here should come from the build underscore spec.yaml file under the output artifacts section, and the name given in the output artifacts section should be used there. So let me copy this and paste this here. So let's click on add. Alright, so our deliver artifact stage has been added. Now remember, the build underscore spec.yaml takes care of running build and pushing the Helm charts to the OCIR repository. For publishing the Helm charts to the OCIR, the credentials and the OCIR path are sent as parameters. So we'll have to set those parameters under the parameters tab. So let's set those parameters over here. So the parameters that we'll have to set are helm underscore repo, helm underscore repo underscore user, user underscore auth underscore token, and helm underscore repo underscore URL. These four parameters needs to be set in the build pipeline under the parameters tab. So let's quickly fill up those parameters here. So you will have to provide the auth token for the user who has the permission to manage OCIR repository. Right. So I have added my auth token over here. Let's click on plus icon to save it and add another parameter. So the another parameter is helm underscore repo underscore user. And here you need to provide the username, including the tenancy namespace. Let me click on add button. And the third parameter is the helm underscore repo underscore URL. So basically we have to provide the complete URL to the helm repository that we created. Let me click on add. And finally, we have the helm underscore repo parameter, where you have to provide the OCIR domain name, which is the region key .ocir.io. So let's click on plus to add this as well. So finally, we have these four parameters created. Okay, so the next thing that we'll be doing is creating a DevOps environment, which will point to our OKE cluster that we have created for this demo. So let's go to the DevOps project and click on environments. Click on create environment. Give your environment a suitable name. Make sure that the environment type selected is Oracle Kubernetes Engine. Click on next. And here you have to select the cluster name. So the compartment is CityDoc and the region is US East Ashburn. And let's select the cluster, which is Mr. DevOps Helm OKE. Let's click on create environment. Alright, so our environment has been created successfully. Alright, so now that we have created the references to our OKE cluster and the manifest to deploy within that cluster, let's create a deployment pipeline. So to create a deployment pipeline, I'll select the DevOps project. Click on the deployment pipelines. Click on create pipeline. Give my pipeline a suitable name. Let's click on create pipeline. Alright, so we have come to the dashboard where we'll add stages to our deployment pipeline. Let's click on add stage. And this time we'll be using the install Helm chart to Kubernetes cluster deploy option. So let's click on the install Helm chart. Click on next and fill up the required fields. Let's give this stage a name. So let's select the environment that we just created. Let's provide a release name. So the release name I'm providing is OKE-Helm. Let's select the Helm chart deploy artifact. So click on select artifact and select the Helm chart to be deployed. Let's also select the values.yaml file, the artifact that we created. So let's select the values.yaml file, which was defined inline. Click on save changes and leave everything as default and click on add. Okay, so our install Helm chart to Kubernetes cluster stage has been created within the deployment pipeline. So now that we have created the deployment pipeline and we have previously created our build pipeline, let's connect them together using the trigger deployment stage in our build pipeline. So let's go to the build pipeline. Let me select the build pipelines. This is the build pipeline that we had created. Let me select it. So now let's add a stage which will let us trigger the deployment pipeline. Let's select the trigger deployment stage and click on next. Give the stage a name and then select the deployment pipeline. So this is the deployment pipeline that we created. Let's select this and click on save changes. And as you can see, the trigger deployment stage has been added to our build pipeline. So let's stop this video over here and come back in the next part of this demo, where we will see the CI/CD pipeline in action and see how the Helm chart is deployed using the CI/CD pipeline into the OKE cluster. So welcome back to this part 3 of demo on using Helm with OCI DevOps to deploy to OKE. So far, what we have done is we have created the build pipeline and we have created the deployment pipeline, and we have connected them using the trigger deployment stage in the build pipeline. Now we'll trigger the build pipeline using the start manual run button on the top right. This manual run will use the latest commit of our primary code repository. Alright, so let's go ahead and start the manual run. Alright, so when you click on the start manual run button, you get to see the parameters. In case you wish to change the parameters, you can always change the parameters over here. For us, the parameters are accurate, so I'll just go ahead and click on start manual run. Alright, so as you can see on the left hand side, we have this flowchart which indicate the different stages that will be executed in sequence. In the middle, we have the build run progress window, and on the right hand side, we have the log windows where we can observe all the logs. So the first stage that will execute is the managed build step stage, where a build runner will get provisioned and which will execute all the commands specified within the build_spec.yaml file. In the meanwhile, let me take you to the container registry and show you that within our Helm repository and the container image repository, there are no images present at this moment. So when this managed build step will get executed, we will be able to see a Helm artifact present within the Helm repository, right? And once the deliver artifact stage get executed, we will be seeing the container image within the container repository. Alright, as you can see, the Helm build has completed successfully. If I go back to the container registry and select the Helm repository, we can see the Helm artifact present over here, right? And let's wait for the deliver artifact stage to get complete. Once that happens, we will be able to see an image, Node.js application image available within this repository over here. Again, let me take you to the Cloud Shell, and let me also show you that currently there are no Helm releases deployed on the OKE cluster. So for that, I'll be firing the Helm list command. And as you can see, there's no Helm release currently deployed on the OKE. So once our deployment pipeline executes successfully, we should be able to see a Helm release with the name OKE-Helm available within the OKE cluster. Let me minimize this. Let's get back to the build pipeline. Let's wait till the deliver artifact stage completes. Alright, so our deliver artifact stage has completed successfully. If I go to the container registry and I refresh this repository, you can see the image has been created. Right, so let's get back to the build pipeline, and now the last stage, which is the trigger deployment stage, which triggers the deployment pipeline, has also completed successfully. Let's go to our deployment pipeline and click on the deployments to see if we have any deployments in progress. Right, so this is the deployment that is in progress. Clicked on it, and as you can see, the deployment is currently installing the Helm chart to the Kubernetes cluster. So once this deployment pipeline executes successfully, we will have our Helm release deployed in the OKE cluster, and we'll be able to access the application, the Node.js application that we are deploying. And let me tell you, in case of any errors or failures, you can always refer to the logs and figure out what went wrong. Alright, so the deployment pipeline has succeeded, and we will have our Helm release available within the OKE cluster. So let me go to the Cloud Shell and let's type Helm list again to see if we have the Helm release deployed. Alright, so we have the OKE-Helm release which is deployed on the cluster. Now you all know that the application that we deployed on this cluster uses a service of type load balancer. So we will be able to access that application using a public IP. So the kubectl command that we'll be using to find the load balancer's IP is kubectl get svc. This prints the service name, which is of type load balancer, and its external IP. We can also fire a kubectl get all command to see all the resources. So we'll use the kubectl get all. As you can see, currently we have these 3 pods deployed on our cluster. These 3 pods are of the deployment OKE Helm node service, which says 3 of 3 is ready. And again, the service that is deployed is OKE-Helm-node service of type load balancer with this external IP. And the replica set that is deployed for this deployment is 3. Basically, it says 3 are desired, 3 is the current, and 3 is ready. Right? So if you remember from the values.yaml file that we had declared as an artifact inline, we had specified the replica count as 3 and set the service type as load balancer. Right? So let's copy this external IP and hit this IP. Alright, so this is our Node.js application which says welcome to the Oracle Cloud DevOps example. So with this, we come to the end of this 3-part series on using Helm with OCI DevOps to deploy an application to OKE cluster. I hope you enjoyed watching these demos. See you in the next lesson. Thanks for watching. Welcome to the lesson on Helm chart deployment with provenance and integrity in OCI DevOps projects. I am Mahendra Mehra, your senior OCI instructor with Oracle University. In this lesson, we'll provide an overview of this new feature, discuss its purpose and importance. So let's dive in. Let's start by understanding the challenges. Enterprises face significant challenges in maintaining the integrity of applications deployed on Kubernetes cluster. Helm charts, integral to the deployment process, lack a mechanism to verify their integrity before deployment, leaving enterprises vulnerable to potential risks. To address this issue, a robust solution has been developed. This solution ensures the integrity of Helm charts by verifying their source and integrity before deployment. Leveraging trusted build sources such as OCI DevOps pipelines or Helm itself, this solution introduces new features to the OCI DevOps Helm stage, enhancing the integrity assurance process through Helm provenance and verify mechanisms. Let's understand Helm provenance in greater detail. Provenance refers to the history or origin of something. In the context of Helm, provenance is a record that provides information about the creation and source of a Helm chart. It includes details such as the chart's name, version, maintainers, and any digital signatures or checksums to ensure its integrity. When a Helm chart is packaged, Helm creates a provenance file alongside it, capturing metadata about chart's creation and the signing party. This provenance file serves as a record of authenticity and integrity. Now let's understand Helm Verify. Helm Verify is a command that allows users to verify the integrity and authenticity of a Helm chart before deployment. When running the Helm Verify command, Helm checks the provenance file associated with the chart to ensure it has not been tampered with or modified since it was packaged. It verifies the digital signatures and checksums to confirm the chart's authenticity and integrity. If the verification process succeeds, Helm considers the chart to be trustworthy and safe for deployment. If verification fails, Helm raises a warning or error, indicating that the chart may be compromised and should not be deployed. Together, Helm provenance and verify mechanisms provide a means to establish trust in Helm charts by verifying their authenticity and integrity, thus enhancing the security of Kubernetes deployments. Now let's take a look at how Helm attestation works. To ensure the integrity of Helm charts, Helm attestation employs the Helm command line tools provenance and integrity features, requiring a valid PGP key pair for verification. This process involves packaging and signing Helm charts with a PGP key pair, creating a provenance record stored alongside the packaged chart. The chart and provenance are then pushed to the OCIR for deployment. OCIR here stands for Oracle Cloud Infrastructure Registry. Optionally, the public key part of the key pair can be stored in OCI Vault for verification during deployment. When deploying, OCI DevOps retrieves the chart's provenance and verifies its integrity using the specified public key. If verification fails, the Helm chart isn't deployed, ensuring the security and reliability of the deployment process. With this, we come to the end of this lesson where we saw this new feature on Helm chart deployment with provenance and integrity. This lets you verify your Helm charts to ensure they come from trusted sources and remain unaltered. I hope you enjoyed this lesson. See you in the next one. Thank you for watching. Welcome to this lesson on continuous testing and OCI support for external tools. Before I go on to discuss continuous testing, let's think about this. If an automated pipeline is handling the software release process, is there still a chance to test the code before it's made available to the end users? Do I still need testing? The answer would be a definite yes. Adopting a pipeline does not mean software testing should be sacrificed to streamline the release process. The very basis of DevOps pipeline is to make the release process reliable and easily repeatable while reducing the chances of errors, delays, and any sort of miscommunication. New or existing automated tests can be easily and smoothly integrated into the pipeline. Unit tests, smoke tests, regression suits can all be run as part of a release pipeline. As you progress further in the pipeline, the test automation spans further from the code level into the areas like API testing, performance testing, load testing, and endurance testing. Overall, the highlights of continuous testing are that it should be part of your continuous development process. Doing so will help identify bugs early in the SDLC and will reduce number and complexity of errors. Testing, which are repetitive in nature, can be automated to speed up the execution. In this way, continuous testing supports the DevOps goal of speeding up software delivery process to deliver high quality software to the end users. Testing can span every stage of your software development life cycle. The blinking stars on the diagram shows where you can automate testing in your SDLC. Each step of the SDLC involves different forms of testing. This minimizes backtracking in the case that you have detected an error. Again, as you see testing is carried out at different stages, it is no longer the responsibility of one particular team. Shared testing responsibilities allow everyone to understand the impacts behind each change. Let's walk through a sample scenario. Say several developers have reviewed and approved a code merge to the working branch of a code repository. Once the code is merged, the CI/CD pipeline picks up the changes in the code repository and tells the build runner to build the code. If the build is successful, the code is ready to be deployed by the CD pipeline. Unit tests should be run by the build server as a sanity check. Then, a suite of automated software tests can be kicked off against the successful build as a further check that the code changes have not broken any existing feature. If any of these steps fail, the pipeline will notify the responsible parties that it's breaking the build, and the deployment is then terminated. On the other hand, a successful run will result in deployment to production environments. Whether you are migrating on-prem workloads to OCI or developing new applications on OCI, you can use the OCI DevOps service to simplify your software delivery lifecycle. One of our DevOps tenets is to improve the developer experience for OCI developers, regardless of what CI/CD toolsets they use. Customers invest in their DevOps tooling to gain speed and reliability of software delivery. Our OCI DevOps works with the customer's existing DevOps tool choices like Jenkins, GitLab, GitHub, Spinnaker, and the list goes on. You might also want to move an existing application from on-premises or another cloud to OCI. The OCI DevOps service has the flexibility to integrate with your existing CI/CD workflows. If you are migrating and want to keep your existing CI workflow, you can move the deployment process to the OCI DevOps and trigger a deployment from an existing CI pipeline to orchestrate your release steps with the OCI DevOps deployment pipelines in the Oracle Cloud. Let's take a look at the external tools and plugins that are supported on the OCI platform. The first one is Chef Knife plugin. We all know Chef is a very popular tool that helps us provision infrastructure as a code. The Knife OCI plugin allows users to interact with the OCI infrastructure through the Chef Knife. We have the Ansible collection that makes it easier to provision resources in the cloud infrastructure through Ansible. The Grafana plugin makes queries to the OCI monitoring services and displays them on the Grafana dashboard. We also have support for the external Jenkins tool such as OCI DevOps plugin. This plugin lets you upload artifacts and run deployments on the OCI through the Jenkins tools. Similarly, we have a Compute Jenkins plugin that allows users to access and manage cloud resources on the OCI through their external Jenkins tools. We have Terraform provider that helps you connect Terraform to a given OCI service in order to manage infrastructure as a code. Also, we have a Terraform Kubernetes installer that helps you manage Kubernetes installation on the OCI infrastructure through Terraform scripts. Let's look at an example on how you can bring your CI to integrate with the CD for automation. Jenkins is a popular product for automating the continuous integration and continuous delivery and deployment pipelines for workloads in the Oracle Cloud. In this architecture, Jenkins is hosted on OCI to centralize build automation and scale the deployment by using the OCI registry and the container engine for Kubernetes. GitHub is used to manage source code, and GitHub provides a webhook integration so Jenkins can start running automated builds and tests after each code check-in. A sample web application is deployed as part of the CI/CD pipeline, which end users can access from the container engine for Kubernetes cluster. Note, a Jenkins plugins for OCI DevOps deployment is available to trigger a deployment pipeline as part of the Jenkins build, which we already saw in the previous slide. When the Jenkins builds come to the point where the software that was built, tested, QA'd, and registered in an artifact repository is ready for actual rollout on the OCI. The plugin allows easy triggering of the deployment pipeline set up in the OCI DevOps. Existing build pipelines can be integrated in this way with the OCI native benefits offered by the OCI DevOps. To wrap up our discussion in this lesson, we understood how the continuous testing is a way to boost, speed up, and support the DevOps CI/CD pipelines. We also saw how well OCI DevOps services integrate with well-known external DevOps tools, making it easier for software teams to pick and choose right combination of tools and services as per their business needs. I hope you've had a great learning experience. Thanks for watching.
Hello, I'm Orlando Gentil, and in this course I will show you how infrastructure as code can be used with OCI. First of all, what is infrastructure as code? Infrastructure as code is a practice that involves managing and provisioning computing infrastructure through machine-readable configuration files rather than through interactive configuration tools. Automating infrastructure management enhances efficiency by reducing manual tasks and optimizing resource utilization. Consistency refers to maintaining uniformity and stability in process, configurations, or actions, ensuring reliability and predictability across operations. Scalability refers to the ability of a system or application to handle increasingly workloads and adapt to change demands without compromising performance or reliability. Our first objective is to understand the basics of Terraform. We will start by exploring what Terraform is, why it's important, and how it fits in the world of infrastructure as code. We will cover the core concepts of Terraform, including providers, resources, and state, how to write basic Terraform configuration files, and a typical Terraform workflow: init, plan, apply, and destroy. The second objective is to dive deeper into using Terraform specifically with Oracle Cloud Infrastructure. Here we will learn how to configure Terraform to interact with OCI, explore the various OCI resources that can be managed with Terraform, such as compute instances, networking components, and storage, implement real-world examples, and use cases to solidify your understanding. Our final objective focuses on OCI Resource Manager, which is Oracle's managed service for Terraform. We will understand the benefits of using OCI Resource Manager, learn how to create and manage stacks using OCI Resource Manager, and explore advanced features such as drift detection and automation workflows. By the end of this course, you will have solid understanding of Terraform basics, know how to use Terraform with OCI, and be proficient in leveraging OCI Resource Manager to manage your infrastructure. Let's get started and dive into the world of Terraform and OCI. In this lesson, we will explore the fundamental concepts of Terraform, a powerful infrastructure as code tool by HashiCorp. Terraform is one of the most popular and versatile tools in the infrastructure as code arena. Let's look at some of its benefits that led it to this position. Terraform automates the provisioning, updating, and destruction of infrastructure resources, reducing manual effort and human error. It ensures consistent infrastructure configurations across development, testing, and production environments, promoting reliability and stability. Terraform supports scaling infrastructure resources up or down based on demand, making it suitable for dynamic workloads. Infrastructure code written in Terraform can be stored in version control systems like Git, enabling versioning, collaboration, and change tracking. Terraform works with various cloud providers and on-premises environments, allowing for a unified approach to infrastructure management. It supports modularization through reusable Terraform modules, making it easier to manage complex infrastructure configurations. Terraform provides a clear audit trail of infrastructure changes, enhancing transparency and compliance efforts. After looking at its benefits, let's shift gears and start working on Terraform essential concepts. First, Terraform commands. These are the instructions we give to Terraform to perform various actions on our infrastructure. We'll cover commands like Terraform init, Terraform plan, Terraform apply, and Terraform destroy. Next, providers. Providers are plugins that allow Terraform to interact with cloud providers and other APIs. They define the resources and the data sources that we can use. Resources are the core components of our infrastructure, representing services like virtual machines, databases, and more. We'll look at how to define and configure these resources. Variables help make our configurations more flexible and reusable. They allow us to parameterize our configuration files, making it easier to adjust settings without modifying the core code. Outputs provide a way to extract and display information from your Terraform configurations. They are useful for sharing data between different parts of your infrastructure or simply summarizing the state. Modules group related resources together into reusable packages, promoting code reuse and organization. We will see how to create and use modules to streamline our configurations. Finally, state. It is how Terraform tracks the current status of our infrastructure. The state file is crucial for managing changes and ensuring consistency across deployments. By understanding these Terraform concepts, you will be well equipped to manage and automate your infrastructure effectively. Stay tuned as we dive deeper into each topic. As those concepts are key for understanding Terraform, they will be individually presented with more details. Thanks for watching, and see you in the next lesson. Hello and welcome. In this lesson, we will cover the Terraform commands. The Terraform command line interface is a tool used to interact with Terraform, facilitating the creation, management, and deployment of infrastructure resources as code. The CLI is essential for executing Terraform workflows efficiently and automating infrastructure management tasks. Next, I will list some of the commands we will use in this course, but bear in mind that the list is longer. First, we have the version command. This command simply shows the current version of Terraform you are using. It's helpful to ensure you are running the expected version, especially when working in team environments. Next is init. This command prepares your working directory for other commands. It initializes the backend configuration and downloads the required provider and modules. Think of it as setting up your workspace for Terraform operations. Then we have validate. This command checks whether your Terraform configuration files are syntactically valid and internally consistent. It's an essential step before planning or applying change to catch any errors early. Moving on to plan. The plan command shows the changes required by the current configuration. It generates an execution plan, allowing you to review what will happen when you apply the configuration. This step helps you ensure that the changes align with your expectations. Next is apply. This command executes the actions proposed in the execution plan generated by Terraform plan. It creates, updates, or deletes resources to match the configuration. Apply is where your planned infrastructure changes are realized. After that, we have destroy. This command is used to delete all the resources defined in your Terraform configuration. It's useful for tearing down infrastructure that is no longer needed, ensuring a clean and controlled removal of resources. Then there's output. This command is used to extract and display the output values defined in your root module. Outputs are useful for sharing data between different Terraform configurations or simply summarizing the state of your infrastructure. Finally, we have fmt. This command reformats your configuration files to the standard Terraform style. It helps maintain consistency and readability in your code, making it easier to collaborate with others. By mastering these Terraform commands, you will be well equipped to manage your infrastructure efficiently and effectively. Thank you for watching, and see you in the next lesson. Hello and welcome. In this lesson, we will cover Terraform variables. Variables in Terraform allow us to make our configurations more dynamic and reusable. They enable us to parameterize our configurations, making it easier to manage and modify our infrastructure setups. Let's look at an example of how variables are used in Terraform. Here we define a variable named compartment_id. This variable has a description, type, default value, and validation rules. The description helps in understanding the purpose of the variable. In this case, it describes that the variable is the OCI compartment OCID. The type is set to string, meaning this variable will hold string values. The default value, default_compartment_id. This value will be used if no other value is provided. We have a validation block that checks if the length of the compartment underscore ID is greater than 0. If not, it returns an error message saying compartment ID must be provided. This ensures that the variable is always set with a valid value. Next, we define another variable called availability underscore domain. This variable only has a description stating it is for the OCI availability domain name. On the right side, we see a resource block for an OCI instance named example underscore instance. Here's how we use our defined variables within this resource. We reference the availability underscore domain variable using var.availability underscore domain. This allows us to dynamically set the availability domain for our instance based on the variable's value. Similarly, we use var.compartment underscore ID to set the compartment ID for the instance. This ensures that our instance is created in the specified compartment. Using variables, we make our Terraform configurations more flexible and maintainable. We can easily change the values of these variables without modifying the resource definitions, which simplifies the management of our infrastructure. A terraform.tfvars file is used to set the values of variables in your Terraform configuration. This file allows you to separate configuration data from your infrastructure code, making your setup more flexible and easier to manage. On the left side of the slide, we have an example of a terraform.tfvars file. Here we define values for compartment underscore ID and availability domain. On the right side, we see a resource block on the OCI instance named example instance. Here's how the variables defined in the terraform.tfvars files are used within this resource. The compartment ID variable is referenced using var.compartment underscore ID, and it takes the value defined in the file. The availability domain variable is similarly referenced using var.availability_domain. Using Terraform.tf_vars files helps in maintaining clean and manageable Terraform configurations, enabling you to efficiently handle different deployment scenarios. Understanding and using variables effectively can greatly enhance the scalability and adaptability of your Terraform configuration. Stay tuned as we continue to explore more Terraform concepts in our upcoming lessons. Thanks for watching and see you in the next lesson.